Okay, without taking up much of your time, hello, I'm Meenakshi. I go by Meena. I'm a developer relations engineer at Postman. I've been working with my very lovely boss who unfortunately couldn't be here at the conference, Doc Jones, on GraphQL at Postman. So let's talk about rate limits in lightning speed. Okay, so we'll first explore, just to introduce what rate limiting is, and then what rate limiting means for GraphQL APIs, and the challenges and the considerations that set it apart from traditional approaches. And then I'll also share some practical techniques for rate limiting for GraphQL. And then I'll leave you with a few real-world examples and APIs and how they do it, and what you could expect on the road ahead. That's enough ground for 10 minutes. Let's get started. Okay, so if you weren't familiar with the term before, with the recent announcements about Twitter, X, or Reddit on their API rate limits, I'm sure you must have heard about them. So a server has limited resources, and all the users of an API are competing for those resources. And it's highly likely a user or a group of them can start to monopolize the system's resources. And you may find yourself falling off a cab even if you did have a seat before. And that is unfair. So this is where rate limiting comes into play. It restricts the requests a client can make within a given time frame. So that ensures fair usage of the API, and it also prevents from other clients having a poor experience of the API. Yeah, this is a sweet little quote I picked up from the Shopify blog. Which just summarizes that rate limits are extremely important to ensure platform stability. Okay, now coming up to the challenges. So we've all learned over the course of the 2 days, if we didn't already know, that GraphQL places the power in the hands of the client. So it enables you to ask exactly for what you want, maybe details about a product, the name or the price, but also, like in this example about the reviewers and the content of those reviews and related products. So basically, as a client, we have a lot of flexibility to ask for whatever we want, which empowers us as clients, but it also poses serious challenges for an API provider from the context of rate limiting. Like in order to resolve the query that's there, there may be calls to other APIs too. There may be a separate backend service for rating. So the query isn't as complex as, say, a query that requests the price of a single product. So different fields and nested relationships in queries result in varying resource consumption. Implementing effective rate limiting requires accounting for this variability so that you can assign appropriate limits based on the impact that each query has on your server. Okay, the number of requests then is probably not a good representation of the load on the server, or a measure that takes into account the nature of the request. So we need to come up with a measure that takes into account the nature of the request, because the requests are so different from each other. How can we do that? Query cost analysis. So query cost analysis is one approach. What query cost analysis does is it assigns a weight or a cost to your request, and that's based on two important measures. So there's type complexity and resolve complexity. And I didn't know about these terms earlier, but I just found there's a paper that sort of explains this entire thing. It's called a principal approach to GraphQL query cost analysis. Yeah, coming back to it, so type complexity reflects the size of the data retrieved, and since not all types are equal. And the resolve complexity reflects the execution cost, which includes the network cost or the cost of retrieving those values. And so some large queries are accidental, and if you have a measure of the type complexity, it would permit you as a client to understand the potential size of the response before issuing the queries, which reduces the accidental service and network costs. Also, as a measure of the effectiveness of this technique, again, something I picked up from the Shopify blog, this image. So you can see that the calculated query complexity and execution time, both of them have a linear correlation using this method. So there are multiple techniques which you can use to apply query cost analysis. One of them is static query cost analysis or static cost analysis. What this does is it prohibits the server from even beginning the query execution on queries that the server deems risky. And since it's before the execution, so the cost is at best an upper bound or a prediction of the actual cost. And before execution, static analysis is usually performed on the gateway or proxy or even like middleware on the server. The next one is dynamic cost analysis. This one is performed directly in the execution engine. And that's also why it's the most precise type of cost analysis. The key benefit in this method is precision, but the primary downsides are that you need to adjust the execution engine and need to wait till like you're well underway the execution and you have maybe already performed actions such as reads and writes to the data before you actually know the cost. Okay, so the third one and the last one is response cost analysis. So since it's response, which means it comes after the request has actually been executed, which is too late because we cannot like save the resources after it's already been executed or protect them. But when you do analyze the response, it can help us charge or account for the cost. And that would impact the way the clients do the future requests. So this method is useful to get a more accurate cost. And this approach becomes particularly valuable when your team lacks direct control over the GraphQL server. So for instance, if you are a part of a team which doesn't have access to the GraphQL server, so you can't do this in the execution engine, but you're tasked with responsibilities like rate limiting or broader API governance. Response cost analysis can serve as a reliable alternative to dynamic cost calculation in those scenarios. Okay, I'll go over these quick. So these are a few key things to keep in mind while implementing your rate limiting technique. One is easy to rule out inspection. It also consumes resources. It needs to be accounted for. Pagination. A request for, say, 100 repositories is not the same as the cost for 5 repositories. So pagination definitely impacts the calculation that needs to be taken into account. And the actual query cost can differ from the expected query cost. So you need to also take care that the client should be refunded if the actual response is less than what was expected. And this is funny. So calculating the query cost also increases the complexity. So there needs to be some accounting for that too. Like the GitHub docs actually encourage you to manually calculate the cost instead of requesting the fields that provide the rate limit information, because that might again add to the cost of your total query. Okay, a few famous examples from public APIs that we have. So you can see Shopify assigns points based on GraphQL types. You can see mutations are more expensive than queries. They involve a lot of writes, so they're marked as 10 points. Yeah. Again, how GitHub does it is GitHub performs static analysis on the query. So the total number of nodes are calculated, and this is essentially for thread protection to protect against recursive queries or the queries that exploit the depth of the API. For dynamic analysis performed in the engine, you can see how GitHub does it is based on the total number of requests that are calculated. And that's how the total cost is evaluated. Yelp uses a response cost analysis technique that we discussed earlier. The Yelp API limits daily access based on how much data is actually returned. So each type, like a review or a location, are assigned different weights. So like maybe querying a business involves a lot of probably calls to the backend or increases the complexity. So the cost for like querying a business is probably more than the others or 10 points. Again, this may not be necessarily based on the number of fields that your query actually returns, but also how the particular type is resolved. Okay, so just to summarize, just like relationships, there is no right answer for cost analysis. We saw in the examples, all of these public APIs use a combination of static and dynamic, or the response cost analysis. Again, rate limits are restrictions, so they may not be perfect or right. So evaluating which approach works for your use case is a process. Lastly, I'll leave you with what you can look forward to, what the future holds next for rate limiting. So compilers can help improve performance by optimizing GraphQL queries, and they also improve the security. They're also sometimes responsible for implementing rate limiting more efficiently. And they can make it easier to maintain the API by abstracting away all the details of rate limiting. So it can free you up as a developer to focus on other aspects of the API, such as the features or fixing new bugs. The Apollo compiler is written in Rust, and that includes provisions for defining recursion limits. Okay, the next one is the bug that we've all been bitten by, AI, which is the second strategy, which is machine learning. Machine learning methods can predict query costs with high accuracy. The model can learn patterns from the traffic and accordingly produce optimized rate limits. A paper learning GraphQL query cost, in fact, proposes this as a viable solution. I'm just going to let it be for a second to absorb. Okay, yeah, we're done with the lightning talk. Before I actually end this and leave you all, I have spent, along with my boss, Doc Jones, a lot of time building these concept cards. So it's our attempt to be able to explain GraphQL concepts. There's actually physical cards that we've printed out that are at the Postman booth. So feel free to stop by and collect them. But there's over 40 concepts, and we're still building more that are on Airtable, which you will find after you scan this QR code. So stop by the booth. Am I done? Any questions? Oh yeah, of course, yeah. 3, okay. This one? Okay. Okay, yeah. So the entire presentation is actually available on the Sched tool, I think sched.com, like where the rest of the schedule is. If you just go over to the speaker profile, you'll be able to find the entire presentation. So you can have at it. Okay. Thank you so much.